Draw the displayed formula of 1,1,2 trichloro 1,2,2 trifluoroethane. So the first thing to note, ethane has got 2 carbons, so each carbon will have 3 bonds. There's 6 bonds coming off, and there's trichloro 3 Cl's, trifluoro 3 F's on ethane. So if there's 2 carbons each with 3 bonds, 6 bonds in total apart from the bond between them, so it's going to look like this. There's going to be 3 chlorines, 3 Cl's, 3 F's, and 1, 1, 2 for the Cl's. If this is carbon number 1, 1, 1, 2. So 2 at number 1 and 1 at number 2, and vice versa. A fluoro, 1 fluoro at number 1, carbon number 1, there's the fluoro, and 2 fluoros then at number 2. So 1, 1, 2, 1, 1, 2, carbon number 1, carbon number 1, carbon number 2, trichloro, 3 chloros, 3 Cl's, 1, 2, 2, an F at carbon number 1, and 2 F's, an F and an F at carbon number 2, trifluoro, 3 F's on an ethane backbone, an ethane chain. Write 3 equations to show how 1,1,2 trichloro 1,2,2 trifluoroethane, so this chemical was banned for use as a refrigerant, how it reacts with the ozone layer. So I'm just going to show you this so I can talk you through it. So what you've got is, you've got CCl2F, CCl2F, and then you've got CF2Cl, CF2Cl. Now what actually happens is, during the initiation reaction, so to start off with then, a Cl dot is always made, a chlorine radical. Now the chlorine radical can either be, the Cl can come from here, or here, or here. It doesn't really matter. And you're going to make something. Let's assume it comes from here, so this is gone. So I'll have CCl2F, CCl2F, and I'll have CF2, CF2, and then this Cl is the one that's gone. The 2 electrons in there, one's gone onto the Cl, and one has gone on to the C. They've split, so one's gone one way and one's gone the other way when that bond has been broken by UV light. So I should really put UV light above the arrow here to show that it's UV light which is providing the energy for that bond to break and an unpaired electron to go onto the Cl and an unpaired electron to go onto that C. Now I've not drawn, you can see the unpaired electron there on the Cl, and there isn't one on this C. It's this C that should have the dot, because it's this C that's lost the Cl. This C here has only got F2, it's got these 2 F's remaining. It's short of a bond, it's not got enough bonds, and so that electron from the bond has gone on to the C when that bond's broken, so that should have a dot on it here. If you'd done it the other way around, if you'd lost a C from here, that would have been okay. You could have C dot, C dot, F, Cl, CF2, Cl. That would have been okay as well. The next stage is that this chlorine radical that's very reactive reacts with some of the ozone. You need to know that ozone's O3. And O3, there's 2 kinds of oxygen, O3 ozone and normal oxygen O2. So the only thing that this can turn into is O2, and then you can work out what's left. Well, I've not used a Cl. I've not used one of the O's now because there's 3 there and there's only 2 here, so there must be an O, and the dot's got to continue. The dot can be anywhere really. It doesn't really matter where the dot is. This is going to react again and reacts with more O3. What's the only thing that O3 can turn into? O2, and I've got 4 O's here, so if I put 2 in front of the O2 it balances the O2, and what I've got left that I've not used a Cl, there it is, and I've not used the dot, and that goes onto the Cl and replenishes the Cl. That means that this is a chain reaction. That Cl that's made keeps being remade. It's a catalyst. Which of the following would cause least environmental damage? So the one without any Cl's in. So Cl's can form chlorine radicals if you expose them to UV light. That's got Cl's, that hasn't got any Cl's, that's got Cl's. So B is going to be the one that causes least environmental damage with no chlorines, no Cl's in it. Give the name of compound B. So it's CF3CH2F. So it's a kind of ethane because there's 2 Cl's. it's got 4 F's, so it's not fluoro, it's not difluoro, it's not trifluoro, it's tetrafluoro, and I better say where the 4 F's are. There's 3 of them, 1, 1, 1, 3 of them at carbon number 1 and 1 at carbon number 2. So it's 1, 1, 1, 2 tetrafluoroethane. The boiling point of iodomethane is higher than that of fluoromethane. Explain why, even though the electronegativity of iodine is less than that of fluorine. Well, first of all, iodine is further down group 7. It's low down in group 7, fluorine's at the top. So iodine is a bigger atom, more electrons, more attraction to the nucleus of a neighbouring molecule, stronger van der Waals forces. So the iodine is a bigger atom than the F, so CH3I will have more van der Waals forces than CH3F. On the other hand, the electronegativity of iodine is less than fluorine, so the CF bond here is going to be more polar. This is going to have a delta plus on the carbon and a delta minus on the F, because the F is more electronegative. So that's going to have a more polar bond between the C and the F than the C to the I, because the I is less electronegative, and so going to have a smaller delta minus. So this is going to have more polar bonds, and between the molecules, that's dipole-dipole attractions. So this will have stronger dipole-dipole attractions. So this will have stronger van der Waals forces. This will have stronger dipole-dipole attractions. And then why CH3 molecules have a higher boiling point, it must be that the van der Waals forces provide a greater attraction, are stronger than the dipole to dipole attractions.